next speaker for this session is Riley Duren of the Jet Propulsion Laboratory. Riley is the chief engineer in our Engineering and Science Directorate. He's responsible for the technical cohesiveness of a wide variety of missions. He'll be talking to us about the Kepler mission, which takes our discussion of scale kind of in a whole new direction. Kepler is a telescope, as he'll be explaining, that will help us understand how solar systems form and what the outcome of solar system formation typically is.
Although I've spent the last 10 years in astrophysics, I started life supporting the earth sciences by building instruments. And about 2 years ago, I started moving back into the earth sciences, and I was primarily motivated to do that because I wanted to do something that had more societal relevance. And one of the complaints, or one of the features of pure astronomy and astrophysics is it can be somewhat distant from Earth. But the topic I'm going to cover this morning, thank you, Microsoft. The topic I'm going to cover this morning, looking for Earth-like planets around other stars, is something that's consumed me from 2002 to earlier this year. It's a project called Kepler that I worked on, and see if you can spot the item of societal relevance here, or if nothing else, the sociological implications. So Kepler is NASA's first mission that's capable of finding Earth-sized planets orbiting in the habitable zone of other stars. And a lot of times you'll hear people talk about habitable planets, and there are subtleties here. In astronomy, when we talk about a habitable planet, we generally are talking about a planet that has the conditions that, as far as we understand life, should be conducive to the evolution of complex life. And so the things that we're looking at are primarily a planet that can support liquid water at the surface. Now, there's a lot of science going on in astrobiology, and there's a lot of work being done here on Earth on extremophiles that suggests that may be a very narrow view of life. But our type of complex life, and particularly life defined as complex life and ultimately life that can build technology and communicate, is believed to be dependent on liquid water. And so when I say habitable, I'm talking about planets that might support that. So what is that? Before I do that, I should say that the speculation about are other habitable worlds in the universe out there besides the Earth is age-old. And you can go back to a few hundred years BC. Philosophers were writing about the fact that there must be many planets without any evidence. They were saying there must be many planets in the universe that support living creatures like the Earth. And we so far lack the evidence to do that. So what are habitable planets? Well, the first ingredient, or the first requirement that might support liquid water, is they must orbit in what we call the habitable zone. Now, a lot of people, like myself, stumble over the pronunciation of habitable. And this is a confusing word for some phrase. So a lot of times when we talk to the public, we use the word the Goldilocks zone. Most people really get that. So it's very simple. The idea is your planets that are in the right zone around a star. They're not too hot, they're not too cold, they're just right. So what I mean by that is if you look at our solar system, which has this distribution of inner rocky or terrestrial planets from Mercury out to Mars, to the gas giants from Jupiter on out, and then we have these trans-Neptunian objects, and there's a big debate about which of these are planets and which aren't. But from a simple distance perspective, where the orbits lie around the sun and how close they are to the sun's warming influence, the habitable zone for our solar system really occupies the orbits from about Venus to Mars. So inside that orbit, like Mercury, it's too hot, water boils away. Too far outside that orbit, water can't exist in liquid form. It may be there, but it's either frozen and trapped just below the surface, or it's sublimated away entirely. In the habitable zone, there are other factors for why liquid water can't exist, and they're more complex than just orbital period. For example, Venus and Mars, and they have to do with things like the presence or lack of plate tectonics, and whether large moons help, like our own, help do that. There's very complex reasons behind it. But the first order requirement is, are you at the right distance that you could even have the right temperature regime? The next requirement is the size of the planet. So even if you have a planet that's the right distance from its star to have liquid water, it needs to be the right size. And that is because planets that are smaller than about half of one Earth mass and larger than about 10 Earth masses won't will not support the kind of atmosphere needed to both, again, support liquid water and complex life. And the reason is planets much smaller than about half an Earth mass don't have enough gravity to hang on to the gases we need to form our kind of atmosphere, like Mercury. And planets that are much larger tend to hold on to the primordial elements which you don't want, like hydrogen and helium. That's why Jupiter and Saturn are gas balls. So you want a happy medium. You want something between about half and 10 Earth masses, and that translates to about roughly 1/2 to 2.2 Earth radii. And so you figure out the density of rock. That's about what it works out to be. So again, in the solar system, the planets that meet this criteria are Venus, Earth, and Mars, and they happen to be the three that are also fall within the habitable zone. Now, other solar systems may have a different distribution of planets that meet those criteria, but we don't know because we only have one sample, our solar system. So how does Kepler find planets around other stars? Well, it's actually a very simple method compared to the other methods that we have in our toolbox, and it's called transit photometry. What it basically means is if you've got a star in another solar system, several light years away, and there's a small planet or a large planet orbiting that star, if the orbital plane of that planet happens to be aligned in just the right way, and it crosses the star when you're looking, if you can measure the brightness of a star very precisely, you can see this dip in the light. It's a very simple method in theory. In practice, it's very difficult because this dip in the light at least for an Earth-sized transit, is very small. Now, large planets like Jupiter produce transits that produce about a 1% drop in the light, and they're pretty easy to see. We can do this from the ground quite readily. We've done it for years with the Hubble Space Telescope. Where we know planets are, as I'll explain in a minute, part of the problem is knowing where to look. But if you knew where to look and knew there was a planet, you can measure Jupiter's quite easily. But an Earth, because it's so much smaller, produces a relatively smaller reduction in the light, and it's only about 84 parts per million is the amount of light. So a Jupiter transit's 1 part in 100. An Earth-sized transit is about 1 part in 10,000. And this is actually a photo taken from Earth of our sun with the planet Venus transiting. This happens every so many decades or 100 years. So this is the planet Venus transiting the sun. Venus is about the same size as the Earth. And so this is about what an Earth-sized transit would look like if you were in the solar system looking at it. Now, if you zoom out several light years away, you can't resolve with our current technology spatially the image. So what you're reduced to looking for is just the amount of light, which is the blockage of this obscuration over this disk. So that's what we're looking for. So ground-based methods, again, unless they know where to look, can't find Earth-sized planets orbiting sun-like stars. This is an excerpt of what we call the Encyclopedia Galactica, which is currently about 350 planets that are known to exist outside of our solar system. And it's an interesting thing. If you go to our website and play around in there, you can click on each of these entries, and it'll tell you about how far away it is from Earth in light years, the estimate of the planet mass, usually given in terms of either fractions of Earth's, if it's a small planet, or fractions of Jupiter's, when it was detected, and it'll even show you a view of the orbit, how close it is. Most of these stars that we found to date are using radial velocity. That's where we look at the star from Earth with a large telescope, and we're measuring the Doppler shift of a star. What we're looking at is the gravitational pull of the unseen planet on the star and how that changes the Doppler of the parent star. And that allows us to find fairly large planets quite easily. We can also do transit detection from the ground, but as you'll see, most of these are very large. They're like several hundred, range from several dozen Jupiter sizes to several Earth sizes. And when you do see planets that are about an Earth-sized planet, I'm not sure if I have any on this slide, even when there are a few Earth-sized planets, they tend to be, in terms of mass, they tend to be very close. So, one of the questions when you look at a distribution like this is, am I suffering from selection effect, i.e. I'm selecting out what I can see based on available technology, and that's absolutely what's happening. If you look at most of these planets, they tend to be very large, and or they're very close. We call them roasters. They're in orbits that are on periods as short as days as opposed to years, and so they're in there roasting. And that poses all sorts of problems for theory behind how solar systems form, because that's not what our solar system looks like at all. This is just giving you an example of an entry, one of these entries in the database. This is Gliese 581 E, which is about 2 Earths. Okay, so this meets the criteria of being about the right size. But look at the orbit. This is the orbit of Mercury. This is for if you were to superimpose the orbit of Mercury on this solar system. Here it is out here. And this white line is where this planet's orbiting. So it's inside the orbit of Mercury. It has an orbital period of 66 days. So each year is 66 days. So this thing is roasting. It's literally glowing hot. Okay, so Kepler's designed to find Earth-sized planets in the habitable zone, out in the zone we care about. So right away, this implies we have to look for a while, right? Our planets around our type star, if they're in a habitable zone, are going to have orbits around a year if they're at where the Earth spot is. So you need to look and monitor for several years to see several transits. The Kepler Spacecraft, okay, this is the Space Observatory which we launched in March, and I'll talk more about that launch in a minute, consists of a spacecraft bus. It's this hexagonal structure which is about the width of this table, which contains the communication antenna. This is a half-meter Ka-band antenna that squirts the high-rate data down to the Earth, and we have X-band antennas for uplinking commands and sending engineering telemetry. These little ice cream cone-looking things are star trackers. This is what we use to point the spacecraft coarsely, and I'll talk in a minute about how we point it precisely. And then these are all the different computers and telecommunication, power, propulsion systems. And then most of the spacecraft mass is taken up by a photometer, which is a telescope, and then this wraparound thingy is the solar array. This is how we power the spacecraft. So the photometer, in astronomical terminology, is what we call a Schmidt camera. And what I mean by that is most astronomical telescopes are designed to gather a lot of light, but they do so at the expense of having that means they have a very large aperture, but they do so at a very small field of view. So for example, the Hubble Space Telescope has a field of view which is roughly equivalent if you take a grain of sand and put that over the sky. That's kind of the area of sky that the Hubble Space Telescope covers with a single pointing. So it's impractical to take the Hubble Space Telescope and go do this kind of planet search, because you'd have to raster scan over the entire sky for probably several hundred years to cover the area you need to. It can look very deep, but very small part of the sky. A Schmidt camera, in contrast, is something that has a very large field of view. Kepler has a field of view, in contrast, that if you hold up your two hands and make a box like this at arm's length, that's about 100 square degrees subtended on the sky, and that's the size of our field of view. So when we look at the sky with Kepler, down to our magnitude limit, we see millions of stars in a single look, and we stare at those millions of stars for years. And that's a survey capability that other missions don't have. So that's one thing. So what you see here is the entrance aperture of a telescope. This big piece of fused silica on the front end is what's called a Schmidt corrector. There's no such thing as a free lunch. You can't do this large field without doing corrective, clever things with the optics. What we're doing with the light here is providing an aberration correction. The light comes in through the telescope, hits a large, relatively large 1.4 meter primary mirror. This is basically a light. You're seeing a honeycomb structure here that lightweights the mirror. The light goes back to this focal plane, and I'll show you a zoom view in a minute, which is essentially a very high-resolution camera. And then the data is sent out through, and is digitized and sent out to the electronics on the spacecraft bus. The focal plane is about this big around, okay? So think of your camera, which has a detector chip, which is about the size of your fingernail, depending on your camera. And the focal plane for this thing's about this big. So what it's made up of is essentially 84 1.5 megapixel CCDs. And they're specially designed CCDs with low noise characteristics and the plate scale we need to do the photometry I'm talking about, which I'll get to in a second. But that's what you're seeing here, is you're actually seeing these, each of these little rectangles is two CCDs butted together. So that's what the blue things are. These are the science CCDs. These little bitty CCDs at the four corners in these masked off areas also collect a lot of starlight, but they're used just for fine pointing control. So a key to measuring these very small signals I'm talking about is to have very stable pointing. If you think about it, if I'm looking at a star and I'm monitoring its light, and I'm looking for a few parts per million of change in that light, if the telescope's jittering around too much, it smears the light. And that is equivalent to noise. And so the other thing we have to do is point the telescope very precisely. So this telescope, using these fine guidance sensors, achieves pointing at roughly a few milliarc seconds level, which is equivalent to the Hubble Space Telescope pointing, but again with a large field of view. So now clearly we can't bring down several million stars. We've got a 95 megapixel camera. If we're staring at these stars for 4 years, continuously and trying to bring down all that data, we would rapidly fill up our onboard recorder and clog up the Deep Space Network, which is our communication network on Earth. So what we do is instead we only pick out 100,000 stars of interest, and we put, if this is the focal plane, these are the CCDs projected onto the sky, we put little basically postage stamps or regions of interest around each star, and we only downlink the pixels associated with the star. So a typical star, depending on how bright it is, will have between 5 and, say, 40 pixels that are downlinked. And even when we do that, we've still got enough pixels that we still have to do compression on board because we store this data for a month before we downlink it. That's based on our communication scheme. What I'm showing here is the field of view projected on the sky. So if you look up in the summer sky, you'll see the constellation Cygnus. And some kind of about halfway between Cygnus and Lyra is the Kepler field of view. And again, that's how big it is. And what I want to point out here is this is the galactic arm. What you're seeing here is the arm of the Milky Way Galaxy. And so Kepler's looking slightly out of that, the plane of that. And the reason is that we're playing a balancing act in the selection of this field of view. We're trying to do a census of planets in the galaxy, right? So the idea is to look at a representative slice of the galaxy and based on the distribution of planets and stars you see there, infer what it's like across the rest of the galaxy. The challenge in doing that is if you point the telescope right into the arm of the galaxy where there's a lot of stars, there's also a lot of dust. That's what this dark stuff is, and the flary stuff is in the background is there's dust, okay? And the problem is that tends to obscure background stars. And the problem with that is the deeper you look, large or giant stars in the background, because of their distance, appear fainter. And you can't tell easily from the ground before you select these targets whether they're small stars that are close or they're large stars that are distant. And that's important because, again, we're looking for Earth-sized planets around solar-type stars. Solar-type stars are stars like our sun. They're main sequence dwarf stars, which means that they are fairly garden-variety, long-lived stars. Our type stars live for tens of billions of years, and we think that's important both because of the type of star they are and the elements that would be available to form planets, and the fact that they live long enough for complex life to form. The giant stars that may be hidden, may be confused in the background, those stars tend to not last more than a few million years, and they do spectacular events called supernovas before planets could get up and running. And so what you want to do is point the telescope out of the plane of the galaxy enough that you reduce that confusion problem. You're not looking through so much dust. But you don't point it so far out of the arm of the galaxy that you lose all your stars, right? So there's a very careful scientific balancing act in picking where to put that field of view. This is an artistic view of where Kepler's looking in the galaxy. So we're looking reasonably deep into the galaxy. Our magnitude limit lets us look about 3,000 light years out. So when we start announcing planet detections, they could be reasonably close, a few light years out to 3,000 light years, again in that narrow slice. Okay, so one challenge of observing like this is that we're in orbit around the sun. We need to point the telescope so that we're not looking at the sun. So we're looking out of the plane of the ecliptic. And what this chart is trying to show you is that every 90 days, or about once every season, we have to roll the spacecraft around its bore site by 90 degrees so that we keep the solar array orthogonal to the sun. The focal plane takes this into account. Again, we're designed to look at one field of view continuously for years, and so the focal plane is rotationally symmetric. So we clock at 90 degrees so that every year we come back to putting the same stars in the same place in the same CCDs every year. So how do we get the data to the ground? Kepler currently is several million miles away from Earth. It's in what we call an Earth-trailing heliocentric orbit. So it's in orbit around the sun, just like the Earth. It's kind of like a little dog on the leash. It's slowly reeling out the leash, and it's drifting away from the Earth. So at the end of a 4-year mission, Kepler will be about half an AU, or about 45 million miles away from the Earth. And so to get that data down, with that progressively weakening bandwidth, we have to use NASA's Deep Space Network. So there are 3 sites around the world, one in Madrid, one in Goldstone. This is in the desert north of here. And then the other one is in Canberra, Australia. And there's a telescope array also nearby. And those things pump the data back to JPL, the Jet Propulsion Laboratory in Pasadena, which is the control center for the Deep Space Network. That data is then sent back across the country to the Space Telescope Science Institute at the Johns Hopkins University in Baltimore, Maryland. It does the front-end processing of the science data, and then ships the science data back across the country, back to California, to the NASA Ames Research Center up in Mountain View, California, where the Science Operations Center is, and that's where they do the transit detection and prepare to do great science and publish papers. And then the kind of a day-to-day housekeeping of the spacecraft and the health and safety checking and uplink commanding is done from the Laboratory for Astronomy and Solar Physics at the University of Colorado, which is our control center, supported by Ball Aerospace, which is the contractor that built the spacecraft. So Kepler launched on a Delta II rocket. This is a picture. This is an artist's concept of the Delta rocket. What you see here is the fairing, which contains the Kepler spacecraft with a, basically this is the motor that was used, the third stage, used to get us on our way. And this is a picture with only one half of the fairing installed. So you can get an idea of we filled every available inch of the fairing with Kepler and our kick motor. This is the launch. We had a beautiful night launch on March 6th. In fact, Louise, who had worked on the project for me some years ago, was in Antarctica doing an assignment. So we were sitting there in the control center getting ready to launch, and we get a call from Antarctica. They're having a party, launch party for us, which is probably the most distant launch party we had. So it was a beautiful night launch. You could actually see, this is a time-lapse photo. You can see the departure trajectory to the east of Cape Canaveral, and it actually lasted long enough. You can see the main engines cut off. You can see the solids fall off, and then the second engine relight. It was a beautiful night. Kepler was moving pretty fast. We departed Earth's orbit within a few days. This is the orbit of the Moon. This is the Earth. So within about 2 or 3 days, we departed the Earth system. And these little hash marks are one-day ticks. So you can see within a month, we were quite on our way. This is the first light image taken from Kepler. This is, again, the field of view containing about 4.5 million stars. We're only looking at 100,000. And you may ask, why? How do you pick those 100,000 to start with? Well, we had a very aggressive ground observing campaign that lasted for about 2 or 3 years before launch, where we selected targets that would be used for monitoring to bring down, and that based on a number of astrophysical criteria. Again, this is just pointing out the relative size of the field. This is the Moon, which is about 1/2 degree, giving you some idea of the size of the field of view. So this is the scale of. And these are just some zoomed-in images of some deep sky objects that show up in the field of view. This is a star that it was known before we launched to have a transit, so we definitely put that in our database to look at. So what about the results? Well, the results should be profound. Again, what we're doing is a census, and so these are some plots from a science team on potentially habitable planets, and these are so these would be terrestrial or Earth-sized planets, and these are all the other ones. And these are numbers on this axis, and these are by spectral type of star on the horizontal axis. And so what this says is that we should find hundreds, if our theories are right, we should find hundreds of giant planets. And if Earth-sized common, if Earth-like planets are common, in other words, if every solar system has a Venus and an Earth-sized planet, we should find about 100 in this survey. So that's significant because what it tells us that if we find none, or if we find few, the implications are that Earths are rare in the galaxy. And this gets to the point I said at the beginning of this thing about what are the implications of Kepler. If you've heard of the Search for Extraterrestrial Intelligence, or SETI, there's a famous equation called the Drake equation that an astronomer named Frank Drake came up back in the 60s. And it was trying to address a question that Enrico Fermi asked back during the Manhattan Project over a lunchtime conversation. And it was the paradox of where is everybody? If you do some simple math, the number of stars in the galaxy, and do your own assumptions about how many should have planets and what fraction should have life, why haven't we heard from anybody yet? This is something people struggle with, and there are both sociological reasons for why we haven't, and they're physical. Well, one of the parameters in the Drake equation is what fraction of planets in the galaxy are habitable. And so Kepler will directly answer that question, which is why a number of people from SETI Institute are on the science team. So that's the sociological angle on this. So after 10 days of calibration data, this represents the first set of data on a few thousand stars we took during the first couple of weeks of the mission. We made some detections. And so what you're seeing here is the relative flux of a star. And this star is HAT P57b. And what you see here is this is a very well-defined transit signature of a planet passing in front of a star, and then it's repeating a few days later. This thing has a very short orbital period. In fact, it's so close to the star that it's almost 2,700 Kelvin. And so this is a very hot, this thing's glowing like an ember is how hot this planet is. But that's a fairly large planet. It's a Jupiter-sized planet. But what's interesting about it is if you look at the signature of this, midway between the two transits, again, this is when the planet's passing between us and the star, there's a very small signature when the planet's passing behind the star. What we're seeing here is the eclipse of that planet when it goes behind the star. So that's a relatively smaller signal. This turns out that this signal is about the size that you would expect from a transit of an Earth-sized planet. So this is a very early check to show us that we're getting the precision we need to find Earth-like planets. We haven't found any Earth-like planets yet, or at least if we have, I can't talk about them yet, because our detection protocol is you need to see at least 4 of these detections to say it's statistically significant and has to have the right signal-noise ratio. And then we follow up on planets to make sure that what we're seeing isn't some astrophysical phenomenon like eclipsing binary. So there's a very rigorous protocol. We don't want to make announcements that aren't reliable. So the message here is to stay tuned. The mission will continue for the next 3.5 to 4 years, perhaps as long as 8 years. And as we gather more and more data, you will see announcements come up on the Kepler mission website here, and you'll also see them in Science, which is where this first discovery was published in August. So with that, I'll take any questions.
Questions for Riley?
Just one in the back.
Dan Ellis, Columbia. That last thing, the star, the planet passing behind the star, was that anticipated? Because like once you say it, you say, yeah, of course. But had you been looking for that dip?
The transit, the planet was detected by Kepler, so we didn't know it was there.
Oh, okay.
And so, but once we saw it, yes, you would expect that the planet goes behind this. If you can, the geometry is if you can see the transit, there should be an eclipse. The question of whether you could actually see the signal that small, what you're seeing is a reflected light signature. And so that was theoretically, yes, if we saw a transit of that depth, the instrument's capable of seeing that. And that's confirmation, if you will, it's kind of on-orbit calibration that it's really achieving its sensitivity limits.
And the solid lines we saw there, they were, I mean, what are they based on? Are there some kind of segmental line fit or?
I don't know where my plot went. Which one are you?
So we see a lot of noisy dots, and then there's this nice solid line in the middle.
Right. So, okay, what you're seeing here is this is a zoomed-in version of this plot, right? So look at the units. That's about from 1.0 to 0.994, and so this is zoomed way in. So you're seeing the raw data points. We have a very complex detection algorithm which takes this data and does fits to it. And so what you're seeing here is when we say that we're seeing the way the data are processed is they're folded on 6.5-hour time scales. The reason is that transits, at least for an Earth-Sun analog, take on the order of hours. So, for example, if you had the Earth and the Sun and you're looking at it in a transit, it takes about 13 hours for the Earth to cross the Sun. So we take all this data, which is being collected continuously, and then it's folded at 6.5-hour intervals. So what you're seeing here is this is the raw data. This is the solution for what the transit's doing. There's one in the back, too. Just so you don't forget.
Go ahead. Terry Liddell from Aerospace Corporation. Thank you. That was absolutely fascinating. And the implications for what you find, positive or negative, are just staggering to consider. I had a question about you're obviously looking at a representative sample of the galaxy, and it's relatively small. How confident are you that your results will enable us to make assumptions about the larger galaxy, about the presence or absence of Earth-like planets?
Yeah, that's a very important question. I mentioned earlier, you clearly got to have the right geometry. Now, it would be great if all the solar systems were preferentially aligned, or actually it could be bad if they're in the wrong direction, but it turns out they tend to be random. And so the probability of seeing an Earth-Sun for a randomly located solar system is about 0.5%. It's just the diameter of the planet. I'm sorry, it's the diameter of a star over the orbit. Okay, so think of a dinner plate and whether this thing intersects it. And so to see, if you're going to infer that there are so many planets in the galaxy at a 0.5% detection rate, you need to look at, this is one reason why we need to look at several hundred thousand stars. That said, the question is how much confidence do we have is we're shooting for essentially a 2 sigma detection confidence for a null result. That is, if we find 0, it needs to give us confidence at the 95% level. If we find 0, the implication is, or if we find very few, the implication is we need to build a bigger telescope. Because frankly, the way that I mentioned that we should find 100, the mission is actually explicitly designed for that. There's actually a null result hypothesis that's designed to give you that 95% confidence interval. It says assume there are 2 Earths, or a Venus and an Earth. So it means we can detect down to a certain level. If we find none, it either means we give up and say we're really rare, which I guess it feels. I don't know, how do you feel about that? But the bigger thing is but does that make sense? And so or is it more of a selection effect, and do we need to build a more capable instrument? So either way, there will be a lot of discussion when we get the result.
Okay, I guess it's my turn. Can I possibly ask 2 questions? One is really stupid, and the other one's potentially not. So the first question is: it seems like you generate a lot of data, and you pass it through, across the country and across the continent. So how do you, what kind of computer power or capability does that require? It seems like you also ought to do some major backups.
Yes, it's lots of backups. So the data come down. The data is archived at a number of places. When it comes down to the DSN state, the Deep Space Network stations, that's a long day. At each of these stations at Canberra, Madrid, and Goldstone, the raw data of the level 0 data is archived for 30 days. It's then archived at the Mission Operations Center before it goes to the Data Management Center at Space Telescope. I should mention that there's 2 aspects of a science. One is that the data goes on and gets passed along to the Science Operations Center at NASA Ames, and that's where they detect transits. And the Kepler science team has proprietary rights to the data for 4 years. Until the end of it's 1 year past the end of mission. So 4 years to collect the data, 1 year to process it. So they have proprietary data rights on that data to make their discoveries and write their papers and say what they said. Then the data is turned over to the broader community. Well, the archive, the raw archive, and also the calibrated light curves, we actually do calibrated data, those archives are maintained at the Space Telescope Science Institute in Baltimore as long as NASA stays around. And so there's both the processed results or claimed detections by the Kepler science team, and then there's the legacy data that will be available to the science community for decades. I should also mention that there's other science that's done with the data. There is what's called asteroseismology, or basically looking at star quakes. It's by looking at high-frequency oscillations of light from a star. Stars vibrate. They have different pressure mode acoustic waves, essentially, pressure modes. And you can tell something about the interior structure, and it's very helpful for stellar astrophysics as a proxy. There are other people who are interested in using our high-precision photometry to look at things like eclipsing binary and other astrophysical things. So a small subset of the data is used for that. So does that answer your question? Yeah.
Can I ask another word? Oh, okay. So, this is the stupid question. So this perhaps pertains to what you mentioned before. How do you distinguish the light from a planet that's farther away, that's larger, as opposed to the one that's closer, that's smaller?
Okay.
So you collect 2D images, but it's of 3D space. Right. So how are you able to reconstruct? Because the images that you showed were all 2D images, right? So how do you reconstruct that?
So really, that selection process actually took place before launch, because the whole idea we don't want to find out. We don't want to find out. That's actually a very hard thing to answer. We didn't want to find out 4 years into the mission that we've been staring at 100,000 giant stars, because we totally wasted our resources. And so for 2 years before launch, we took some of the world's largest telescopes that our science team has access to, and we did observing every night we could during the summer when Cygnus is up. And that was basically a stellar characterization program. And the short answer to your question is that there are various ways to decouple magnitude from distance. One of them is spectroscopic. That is that the ground telescopes, they don't use the same method as Kepler. They use multiband photometry, that is looking at different spectral bands and doing subtracting colors, or they do spectroscopy. And using that, astronomers are able to pull out various astrophysical parameters to give them a sense, to decouple the degeneracy between how far something is from how large it is. And that process is basically what's used to subtract out whether it's a giant star or a dwarf star. And that's done a priori.
Okay, we'll take 2 more questions.
Alan Zimmerman, Northrop. Your last comment was if you don't detect anything, you need to build a bigger telescope.
Mm-hmm.
Sounds like you're throwing away a vast majority of your data. Sounds like what you really need is a bigger communication network.
I would disagree with that. The reason, for several reasons. One is it turns out, and I have a reason for that. Let's say hypothetically that we could bring down the entire focal plane. Every pixel. So we weren't throwing away any data. Okay, so let's say that we didn't have a practical limitation. It turns out that we're astrophysically limited. It is that even with the 5 or million so stars that are in our field of view that are within our magnitude limits, we had to really scramble to get 100,000 that provide the right kind of candidate. You see, it turns out that most stars are not like ours. They tend to be larger stars, or they were stars that have properties that are not conducive to finding planets this way. That is, they are very noisy. Cataclysmic variables, or they're a P star, and they're B stars. They're very noisy stars. So the planets would be lost in the noise. So there's a lot of science before we ever launched the mission that went into selecting these targets, and we were hard-pressed to come up with at least 100,000 stars that are good candidates. So even if we brought down every star, I would be hard-pressed to find them without looking at another part of the sky. So another way to ask your question is if we don't find any in this field, should we point and look at another field? And that's a good question. It turns out that the system is designed to support looking at other fields. We could point elsewhere. And we have enough propellant on board to do another 4 years. We can last about 8 years. So that might be that would be an interesting discussion then, is if we see nothing at the end, do we continue to stare for 4 years? Does it mean that they're in longer period orbits and we just haven't seen them yet? Or do we give up on this field and move to another one? So far, the science community's consensus is the right way to do this experiment is to sit and stare at one field and look for more transits as opposed to looking at another one.
Hi, Ravi Kane, RPI. Mm-hmm. Let's say you're successful and you find 100. What do you do then?
Right now, what? So, Louise and I both have been involved in NASA's program of planet hunting for over a decade. We're not doing earth science. And Kepler is actually the easiest way to do this. There are a number of programs on the books for what would you do next. Okay, so the obvious thing is, let's say that we find a bunch of them, we say that they're in the right orbits and the right size. Well, that doesn't tell us that there's actually life there. Far from it. It just says the conditions might be right. So the obvious next step is to go look at the planet in such a way that you can actually tell what's there in terms of chemistry. It turns out there are ways spectroscopically to tell whether there are building blocks of life, like oxygen or ozone as a proxy, methane, CO2, and most importantly, water, are present in the atmospheres. And there's a program called the Terrestrial Planet Finder, which NASA's been working on for well over a decade, and other missions, which allow us to get there in theory. And it's a technology program that's been underway for about 15 years. And that involves essentially flying very large telescopes in space, or constellations of telescopes flying in formations using interferometry to do synthesis imaging to essentially synthesize telescopes the size of a few kilometers across. And those systems, which Louise and I have worked on, which work in the lab quite well, are theoretically capable of resolving the disk of these planets and nulling out the light of a star to see them, and with sufficient spectral resolution to pull out the lines of things like water and methane and CO2. That would be the obvious next step.
Great. Let's thank, again, all 3 of our speakers.